I know, I know. We'll get there. I'm gonna fix it. I'm gonna fix it. Okay, so the way I set this flow chart up might be it's just confusing me the way I set it up. But I'll explain it the best here. You ask this question: is it ordered? Okay, and if you say yes, you're going to go up here. If you say no, it classifies your level of measurement as nominal. Okay. If you're to say yes, then you ask the question equally spaced. Okay. So that's kind of when I made the error a moment ago. I didn't read that question and I went straight to here. Okay. So once you say yes, there was order. Is it equally spaced order? Okay. If the answer to that is no, then you say that your level of measurement is ordinal. Okay. If it's equally spaced, then you come here and say, does zero mean something? Is zero essentially my starting point for my level of measurement? Okay, or a collection of my data, or creation of my data. Okay, so basically, if zero means none, that means like we're doing a length, we're taking a measurement of volume, a measurement of height, something like that. Okay, age. If we have a zero that means nothing, okay, means the amount zero, essentially. If we say yes, then it's ratio. If we say no, it's interval. Okay, and that means so we're saying zero means none, means it means the absence of something. Okay, for instance, on like temperature, when I'm talking about Celsius or Fahrenheit, does zero mean the absence of heat? 0 degrees Celsius, 0 degrees Fahrenheit? No, right? Okay. So that is the situation or an example where zero does not mean none, or zero does not mean the absence of something. Okay. Where if I was in the Kelvin system, Kelvin, absolute zero, does mean the complete absence of heat, right? So in Kelvin, we would be in a ratio. Does that make sense? Okay. So that chart may help. Okay. When you're reading that chart, be careful that you ask the question that you're in, okay, or the box that you're in. But if we're looking at our particular scenario here with our data, we had A, B, AB, and O, right? Those were the types of blood that we're looking at. Are those ordered? Does that order mean something different than this order to us? Or this order? No, that it's not ordered, right? So the answer, no, we go nominal. Okay? Does that make sense? Okay. So when we're looking at this, so we got a level of measurement that is nominal. When you are doing nominal or ordinal distribution tables, they're going to be a little bit more concise tables than if we're using ratio or interval, because there's just less things that we can do with them. The first thing you're going to do is you're going to create what we call a class. And our class is essentially the types right here, okay, for ordinal or nominal data. So I'm just going to type in, I'm just going to go A, B, AB, and O. In some distribution tables, you're going to see a column that says tally. And all that means is that they're going to, it's just a quick way of saying, okay, A, I've got one. There's a second one, just a quick way of counting, right? And the way I do this, especially when I have the raw data, is I make sure that one, I tally it, but then I also cross it off. Does that make sense? Because it sucks, especially if you have like a list of 100 numbers or 200 numbers, or in this case, maybe you have 200 blood types and you go through and you miscount them. If you miscount them, miscategorize them, your entire study is now incorrect. Okay, you've by human error created some falseness of your study. Is that okay with everybody? So just be aware of that. Now, some people might be able to go through here and just count them quickly. But for that purpose of not wanting to make a mistake, I'm going to tally them. I'm going to cross them off. So if I go B, there's 1, 2, 3, 4, 5, 6, 7, right? And then AB, 1, 2, 3, 4. And then O's would be 1, 2, 3, 4, 5, 6, 7, 8, 9. Are we okay with that? Okay. The next then is what we call our frequency column, which is our kind of italicized lowercase f. All that means is that now you're taking your tallies and you can convert those into a numerical representation. Okay, so that's why sometimes some of you might be saying, well, the tally column, that was kind of maybe pointless for me because I didn't need that. With small data sets, maybe you don't. But again, larger data sets, maybe it's a good idea to have that column. Okay, but put it in red there so you may see it, you may not see it. If you're doing this on your own, it's your personal preference. I would just be careful. So next thing we're going to do is, yes. What's that? Yes. Yeah. It's just when I made it in PowerPoint, I just didn't change the formatting of it. One thing that you'll see common is that when you do your frequency column, is that they will have a total, or you will put a total at the bottom of that, just to verify that you know how many data points you have over here. Make sure you've counted them all. Okay, so when I look at this, that's 12, 16, 25. Okay, so that kind of confirms to me I had 25 data points. I have 25 here, and make sure I've got each one tallied. Okay. Next thing you're going to do is the relative frequency, which we said yesterday was F divided by N. Okay, so F for A, or type A, would be 5 divided by N, which was 25. And then B was 7 over 25. AB, 4 over 25. And then 9 over 25. Does that make sense? Okay, now in the chart we saw yesterday, we had a cumulative frequency. Okay, and this is why this type of data, and this level of measurement, creating the distribution table, is sometimes a more concise table than using interval or ratio, is because the way that I set my classes up here, the order wasn't specific, right? Okay, so somebody could have taken the exact same data and created and gotten the same exact relative frequencies, but they could have organized things like this. They could have gone, let's say they went O, A, B, B, and A. So then that would have been, so when they got to their frequency, that would have been 9, 4, 7, and 5. And again, so this would be 9 25ths, 4 25ths, 7 25ths, and then 5 25ths. And now if we did a cumulative frequency, let's just think about, the first one's obviously 5 25ths, but now this next one would be, you guys remember adding those and get 12 25ths? If I was doing that, if somebody had this exact same data and they went this route with their ordering of their classes, this first one would be 9 25ths, and this next one would be 13 25ths. You see how these columns don't match? Because the order of my classes was just random, right? So that's a reason why you might be asking, well, how come in some examples we put the cumulative frequency, sometimes we don't? That would be kind of that deciding factor, because the order in which we create our classes or write our classes doesn't matter. Is that all right? Okay. Now, the next question, the next one we do is going to be using this data. Okay. Again, don't write all that down. Okay. But what we're going to do is we're going to take that raw data. So what this is 50. So I'm an employee or a CEO of a large corporation, and I surveyed my employees, 50 of them. Okay, that's my sample and asked them how many miles they drive to work. Okay, and this is the information they gave me. Now here's my question. Okay, let's go back up to this. If we're talking about miles driven to work, is that information ordered? It is. Okay. The idea essentially is that we've got numerical values. So numerical values can be ordered from least to largest, right? Okay. So yes, are they equally spaced? Okay. Yes. Okay, 1 mile to 2 miles, 2 miles to 3 miles, 3 miles to 4 miles. That interval is the same, right? Okay. Does 0 mean something to me? Okay. Is 0 essentially my starting point in terms of length? Yes. So this tells me I've got ratio level of measurement here. Okay. And another way, yesterday I said a quick way, ratio is used predominantly with volumes, lengths, and masses or weights, right? Okay. And distance traveled to work is one of those things. It's a length. Okay. So this is ratio level. So this is the type of data we prefer. It's the type of data we're going to see the most throughout this course because we can do the more statistical analysis of it. So there's a couple things. This distribution table is going to be a little bit more involved. Okay. Now our classes are not categorical in this case. Okay. Last time they were categories, right? A, B, or O, based off the names of those blood types. Your classes now are going to be numerical. Okay. So instead of calling it just class, a lot of times we refer to this column as our class limits. Okay, so we're going to create a column of our class limits. So I'm going to show you how you create your class limits. Okay, your lowest quantity up here, your lowest piece of data, smallest piece of data, ends up being your, what we call our lower limit of our first class. So what's the smallest data point up here? 1, right? Okay, so I see 1. So that's my lowest limit of my smallest class. Okay. Now we need to figure out, well, how many data points, or what is the range, I guess, of the first class, and then what is that of the next class, and so forth. So this is how we do this. Okay. You're going to try to determine your number of classes that you're going to choose. Okay. Okay. A kind of a general rule of thumb with distribution tables is that you want to have 5 or more classes, but you want to have less than 20 classes. Okay. The more data you get, maybe it's more appropriate to have more and more classes. We try to stay between 5 and 20. Okay. If you do some research on, I could just haphazardly, I want 5 classes. We could do that with this class. We could just say, okay, we're going to have 5 classes. Maybe some of us might, I want to do 6 classes. Okay, do it. You want 7 classes? Do it. Okay. But a lot of times you'll see people with the argument that a safe thing to do is to find the number of classes. You take the square roots of your sample size. Okay. So right here we got the square root of 50. And that gives me approximately 7, right? Radical 49 would be exactly 7, correct? Okay. So that's a good starting point to say that we're going to have 7 classes, okay? But like I said, there's nothing wrong with saying we're going to have 6. And even in this example, because of what we see here in a moment, because our data, even though we've got 50 pieces, we're going to have 7 classes, 1 to 18, because 18 is the largest distance up there. Actually, that data is so compacted, it kind of throws a wrench into our classes here in a moment, and we'll explain that as we work this out. But that I'm going to say we're going to start with 7 classes, okay? Now I have to figure out the class width. So your class width is going to be the data range divided by the number of classes that you've chose. So the data range, okay, range, go back to 7th grade, 8th grade math. Range is when you subtract the largest value minus the smallest value, right? So in our case, we've got 18 being your largest, minus 1, and my number of classes is 7. So we get 17 over 7. So our class width, I think that works out to be like 2.4, something like that. Does anybody have a calculator handy? 2.42. Okay. When you determine your class width and you get a number that is not a whole number, you always round it up. Okay, so our class width, we are going to say, is going to be 3. Is it okay? Okay. So this is what we do next with our class limits. You're going to start here. This was our lower limit of our first class, right? To get the next lower limit, you're going to add your class width to that. So 1 plus 3 gives me 4, right? 4 plus 3 gives me 7. 7 plus 3 gives me 10. 10 plus 3 gives me 13. 13 plus 3 gives me 16. And then my next one will be 19. Does that make sense? Okay. Now, does that give me 7 classes? Does that make sense? Now, this last class is going to start at 19. Is there any data point up there that's going to be in that class? No. So that's when I was talking about the data so compact, and we chose 7 classes. That 7th class is actually going to be 0. So we'll talk about this in a little bit, but we can cancel that one out if we wanted to. Okay. Now, those are our lower limits. Those are our lower limits. We need upper limits for our class, or individual classes. So this first upper limit is going to be 1 before this one. So 1 to 3 is my first class. Does that make sense, everybody? And then the upper limit for the second class is going to be 1 less than that lower limit. And what this is doing is guaranteeing that every single one of these data points should fall in a class somewhere. Does that make sense? So this will be 7 to 9. This will be 10 to 12. 13 to 15. 16 to 18. And this would be 19 to 21. Okay? But again, there's no data up there between 19 and 21. So it's going to be an empty set. There's going to be no frequency, so we really don't need that one. I had, at the onset, I wanted 7 classes. The way it sets itself up, one of those classes has nothing in it. It's the last one that has nothing in it. Does that make sense? Okay. So that's our class limits. Everybody okay with that? Now, sometimes, and this is just the way sometimes procedural things get done in a stats class, and the way people argue certain concepts is that some people say that this should, instead of saying 1 to 3, this should say 1 to 3.9. And then this should say 4 to 6.9. Okay? And that's fine. There's nothing wrong with doing that. It's acceptable. Okay? And what that does is it minimizes the potential of any values that are in that gap of 3 to 4 by falling in no class. Does that make sense? Okay? But let's look at our data. Our data is all whole numbers, right? So even though there is a gap between 3 and 4, and if I went 3.9 to 4, there's still a gap. But 3 to 4, there's a gap of values, a gap of data that we could let slip through the cracks. But look at our responses up here. Are any of our data points non-integer? Okay, so I'm not going to have like a 3.5, right? So I'm not worried about that. We shouldn't be worried about that. Okay, if we had like a 5.1 here, so that's talking about the precision of our data. Our precision of our data is out to now the tens place. I would want to make sure that these are written in terms of tens place. Does that make sense? If it was out to like 5.12 or something, was one of my data points, then that precision of my individual data is out to the hundredths place. So I'd want to make sure that this was out in the hundredths place, and that guarantees that nothing falls through the cracks. Is that okay? Okay. The next thing you're going to do is your tally column, and I'll let you, just to save time, I think we can go through this with just by counting. So then we'll get to our frequency column. So let's go through and calculate the piece of data that fall in the 1 to 3 class. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the frequency of that would be 10. Is that okay with everyone? Okay. 4 to 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Thank you. See, that's why we want to cross someone. You see how easy it is to make a mistake when organizing the data. 7 to 9. So let's see here. I'll circle these in red. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We okay with that? 10 to 12. 1, 2, 3, 4, 5, 6. Is that okay? 6. 13 to 15. So 1, 2, 3, 4, 5. And 16 to 18 should be everything that doesn't have a mark on it, right? So 1, 2, 3, 4, 5. I just want to double check. I'm going to figure out what my N is. Okay. Add these up. So 24, 30, 40, and then plus 10 will give me 50, right? So that confirms to me, even if you guys didn't catch my error earlier, we would have added those up and we got 49, right? And then I'd have to go back through and count again, okay? That would really stink if, 50 numbers isn't that bad, but if I had, 2,000 data points or something like that, that would be frustrating, right? And eventually you'll start to see, okay, if I've got that many data points, why am I doing this by hand, right? If I got 2,000 data points, I'm probably just typing those data points into an Excel sheet and letting Excel or SPSS, which is a stats program, do all this for me because it won't make that mistake. Does that make sense? Okay, so we'll use some of that stuff later. So we got our frequency column. Now we're going to do our relative frequency, which is F divided by N. Let me clean some stuff up here real quick. So F divided by N for each one of these. So this would be 10 divided by 50, 14 divided by 50, 10 divided by 50, 6, 5, and 5. Okay. Now you might argue, well, I should reduce those. I would agree. We should probably reduce those, but I'm not going to right away because I'm going to use my relative frequency to help me come up with my cumulative frequency column, right? And if I reduce them and then I got to add them together, then I've got to come up with common denominators again, right? Does that make sense? So I would be undoing the math that I've already done, and that's kind of silly. So I'm going to write my cumulative frequency. And remember, all you do with cumulative is the first should match up to the first relative. And now here, it's taking this one and adding it to the ones that are above it. So I got 24 50ths. Okay. Then I'm going to add this one to the ones that are above it, which is going to be 34 50ths. Then I'm going to add this one to the ones that are above it. So it's 40 50ths. Then this next one will be 45 50ths. And this one will be 50 50ths. Is that okay? Remember, when we're done, that last cell right there, the last cumulative block should be 1. Okay, and I'll guarantee that you've done it correctly. So now that's our frequency distribution table. And what that is going to do, that's kind of the middleman for us to be able to take our raw data and put it into a table, into a graph, a histogram, or maybe sometimes a line chart or a time series chart or something like that. Does that make sense? So this is going, now we've organized our data. If I present that, if I'm doing a study and I present that as my overall graphic, there's going to be people there that say, okay, well, what is that? That's just a bunch of numbers to me. But if I can make that into a histogram, that might allow somebody that's not all that mathematically inclined to recognize, the disparities between the data here, that will be much more impactful. Does that make sense? Okay, so we take our raw data, we put it here, we organize it, and then we'll talk about, once we've organized it, how do we then present that? Okay. But here I can answer questions about my data now much better with the table than I could here with the raw data. So they might ask me questions. What is, let's say that I've got what percentage or what fraction of employees drive 9 miles or less? Well, 9 miles or less would be everybody in those classes, right? So now I can just go to the frequency, the cumulative frequency, and say, 34 out of 50. Okay? And that's so much easier than going up to my raw data and say, okay, 9 miles or less. Count all that are 9 or less, and then divide by 50, right? Now I've got it. And I can answer, how many people drive more than 10 miles. Okay? Well, wouldn't this be all the people that drive more than 10 miles? Does that make sense? So what I would do, just to make my math a little bit easier, I would look at that number and that one, and if I subtract them, that gives me 16, right? So it tells me 16 of my people drive more than 10 miles, or 10 miles or more. Does that make sense? So you can answer those types of questions a lot easier looking at a distribution table than you can at the raw data. Okay, so we're going to work on those a little bit more on Monday. There's going to be, even when we get to chapter 2, there's when we start chapter 2, there's kind of an understanding that we know a little bit about distribution tables, but we're going to add some stuff to them. We're going to talk about midpoints, If I want to find the midpoint of that first class, how do I find midpoints of classes? How do I find midpoint between any two values? Add them together, divide by 2, right? Okay. So add them together, divide by 2, and that will give you my midpoint. I think in your homework tonight, there's 9 questions. One of the questions asks you for a midpoint of a class, which you just add the 2, the lower limit and the upper limit of the class, divide by 2, it gives you the midpoint. Midpoints are going to be needed for when we draw histograms. Okay. There's something called class boundaries. A histogram, by structure, the bars in a histogram, okay, they should always be continuous. They're always touching each other. Okay, there's no gaps between them. In order to do that, we need what we call class boundaries, which is very easy to find, but that will be another column we add to this table. Okay. In your homework it's on My Open Math. It's more friendly than the other assignments we've done in My Open Math, but you're going to see them use the acronym GFDT. GFDT. It's a grouped frequency distribution table. That's what that's standing in for. Okay, which is exactly what we're doing here. Is that okay with everybody? So you see that and don't know what it means. Grouped frequency distribution table.